Welcome to today's Research Pays Off. I'm now going to hand it over to our speaker for today, Quang Tran.
Thanks, Lauren, so much for the invitations. And then, good morning, everyone. My name is Quang Tran from Michigan Tech, and I'm happy to be here today to introduce my research topics about non-contact technologies for enhancing the earliest concrete pavement. And I hope at the end of the presentation today, I can convince you that the non-contact technologies it can help to determine the concrete set time in situ, and it can support the field engineer in making decisions for the construction activity timings, such as the saw cutting or even the open to traffic. So my talk today is including four parts. In the first introduction, I would talk about the importance of the in situ concrete set times and what are the current research that we've been doing in order to determine the concrete set time in the lab and in the field, and then what is their limitation and challenge, and then what is our motivation in order to propose these non-contact technologies to overcome those challenges of the others existing methods. And then finally, I will talk about some application of these technologies, including you can use this for predicting the saw cutting times, or you can evaluate the curing compound effectiveness. And I will make some conclusion, and then I'm very welcome for any question and comments. So the picture that I'm showing on the left is that the fresh concrete that is done on the ground. And the pictures that I'm showing on the right is concrete already hardened in the form of the concrete pavements. And you can see is that initially, after we mix the concrete, it's still in the liquid phase. It's because that when we mix on the cement and aggregates with waters, but over time, when the cement particles is react with waters, it creating more and more the hydration product, or we call it gels, and this will create a bonding in the matrix that is makes the concrete change from the liquid phase into the solid phase. And the setting time of concrete is the transitions, and the set time is the time that it transitions from the liquid phase to the solid phase, right? However, the set time is not always easily recognized, as you can see. We can easily damage the concrete pavement. Even after the concrete is paved in the shape of the concrete pavements, it doesn't mean that the concrete already set, right? So, furthermore, the set times of the concrete pavements, it influence more activity, construction activity. So it influenced the time that we replace the concrete, and influence the time that we're paving the concrete, because that if we're paving the concrete after it's set, it's become really bad quality for the concrete pavements. And also it's reflecting the time, influence the time that we need to do the texturing in order to create a friction. And the time, of course, in the times is that we have applied in curing compounds in order to ensure that the hydration of the concrete materials. And then finally is the time that we need to do the saw cutting is it's really much depend on the set time of the concrete material. And I will show you later in this slide that how the saw cuttings timing is influenced by the set times. So so what is we have been doing in trying to determine the concrete set time in the lab and in the field. So firstly, it's the very well-known ASTM standards C403, the penetration test. And then this test is very simple and then straightforward in order to determine the set times. All we have to do is just make the concrete sample and then extracting the cement paste, and then do the pin penetrance resistance test. However, one of the steps that we have to follow in this procedure is the wet sieving. So I remember that when I make when I did the wet sieving. So all I do is I showers on the concrete into a big siever, and then with the help of my friends in the lab, we hold we hold the sievers and then keep shaking. We shake it, and then finally we collect the paste. So as you would imagine, following this procedure, um, it's very labor and time intensive. And also this test is kind of like destructive, and then it's not possible to apply this technique in the field. So that's why people trying to come up with the techniques that it's applicable for the field testing. And then one of them is using the UPVs, the ultrasonic pulse velocity testing. As you can see in the middle figure, it's a test setup that the CPTech centers have been trying to determine the setting times in the field. And then what they did is they need to extract a companion sample of concrete cylinders 4x8, and then they use the UPV, and then they use transducer to cap on both end of the sample. However, this process is not really easy, because that we have to use the flexi class in order for the transducers is not in contact with the materials. Uh, and also, in order to ensure the coupling of the transducers and the sample, then we have to use another gel coupling um, to ensure that the energies of the wave traveling from one end to the others during the whole testing process. And then finally, what the UPV give is that the velocity development of the P wave over time. And they use this information in order to determine the final set time of the concrete material in the field. So this test, again, is not directly applied to the pavement. And then you have to extract some material and then put it in the cylinder 4x8 in order to run the test. And another test that also can be used for determining the set time is called ultrasonic wave reflections. So the way it's set up is that they use a mold that they call it the buffer here. And then at the bottom of the buffers, they will attach to uh, uh, a transducer that generates the shear wave. And they will they will put the cement materials or the cement paste into the mold when it's still fresh. And then initially, when the cement paste is not set or in the liquid phase, the the wave that generated from the transducers is not be able uh, to penetrate into the cement paste, because that the bonding between the buffers or the mold and the material is not strong. But over time, when the cement paste is getting hardened and the bonding between the material and the buffer becomes stronger and stronger, then we have more energy will penetrate into the materials, then and then less weight coming back to the transducer. That's why when you see the curve on the right here, you can see initially it's the energies that reflect back to going. Let me see if I have a laser point. So you can see in this plot, like the energies that initially is traveling from the transducer go to the buffer and reflect it back to transducers is pretty high, because there's no much bonding between the cement paste and the buffer. But over time, when the cement paste gets hardened and this bonding becomes stronger, then we have more energies penetrate to the cement material and less energy reflect back. That's why this curve is start to decrease over time. And along this curve, there's some indicator that the author use in order to determine that the set time of the materials. This is very empirical method. So just the summaries that about the existing method that people been using in order to determine the set times, including the pin penetration test in the STM standard, and they use the UPV, and also they use the wave reflection factors that I just showed. Most of them is the advantage are very simple, inexpensive, and then it's very doable in the lab. But they have some challenge is it's very labor and time intensive. It need a companion. It's mean that you have to extract this from the pavement in order to run the test, and it's destructive testing, and all of them is the point testing. It means that you can only test at one specific location, and then you cannot test this use the set used for a different locations because you have to extract another sample from different location in order to run the test. And most of them is very difficult to apply it in situ structures. So so in order to overcome these challenges, so our motivation is in order to create technologies that we can be able to apply it in situ, and it can give us the quantitative measurements in real time. And also we can use this technology in order to measure at any locations that we want to. And then eventually we can have the map of the whole set time of the pavements, um, maybe over miles, not just limited ourselves in specific locations. So that is the motivation of us to create a new technologies. It's called non-contact technologies that I'm going to introduce that used about the principles and some result that we collect in the lab and also in the field. So here the figures on the top left is showing that how that we set up the prototype. So we have it's pretty straightforward also. So we have a train user that we're running at 54 kilohertz, and then it's off have like it's off from the ground from the surface of the concrete pavement, and we sending a wave to the pavement, and this wave it generate a leaky surface wave. Sorry, it is create a surface wave firstly, and then this surface wave it will create a leaky surface wave into the air from the surface of the pavement, and then all we have to do is we have to put a array of a sensor. The reason why I put the array of sensor is in order to make it more reliable, and because sometimes one sensor can like have some problem, it doesn't work, or it collect a different signal. So we have to use the array sensor in order to eliminate some noise um, that can interrupt the result of the measurements. So you can see in this simulation at the bottom here, and you can see this is generating the wave, that the wave generate the wave traveling along the surface is called a leaky called the surface wave or the Rayleigh wave. And then after it traveling, you can see that the gray energies here is the leaky surface wave that it leak from the surface. And all we have to do is we put the MEM sensors um, uh, off the ground in order to receiving the signal that, and then you know that this wave interacting with the materials, and it carries some information about the material too. And we try to capture the signal wave and then correlate it with the material properties that the wave carries. And on the right here is that the setup that we pilot in the field in one of the projects that we try in Tasca, Chicago, Illinois. And I will go into details about in the next few slides. So the principle of the method is based on the phase changing that I described earlier. So right after we mix the materials, um, we make the concrete, and um, because the concrete material is still in the liquid phase, so um, and it doesn't have enough strain or the shear resistance in order to carry the wave. Um, One of the principle in order to have the Rayleigh wave is we need to have two components of the wave, including the longitudinal wave, which is the also called compression wave, and then we have another wave is called the shear wave, um, propagating, and then two components they will combine and then creating the surface wave. And then without one of them, we're not going to see any signal of the surface wave. So that said, it means that when after we're mixing the concrete materials, most of them it's water, and we know that water cannot take the shear. So that's why initially the shear does not propagating in the material yet. But so over time, when the shear resistance or the shear strength in the concrete matrix starts to increase, then we will have some energies of the shear waves, and it is combined with the compressional wave and creating the surface wave. At that point, then we start to receive some signal, and then over time, you know that as the percolation increase, the bonding is getting stronger. Then we have a better, and then higher signal. That's why on the figure on the right here, we can see that the energies of the leaky wave initially is really it's almost zero, and then at some point it's increasing dramatically. So I call this point when it changing the energy is the initial time of the leaky surface wave, or the term is use LR because that R stands for the Rayleigh wave, and LR is the leaky Rayleigh wave. So once again, you can imagine that what happening in the structures like this schematic show. So on the left figures is I have all the components that within the um, concrete matrix, including we have the the black circle here is the aggregate, and we have a cement particle, and of course we have some air void, and the surrounded is the water. And then over time, when all the cement hydrations, on the cement particle here, when they reacting with water, and they will develop from they create some hydrated cement, which is the gel surrounding the cement particle. And over time, this hydrated cement is getting more and more. It's creating the bond to the aggregate and then to others cement particle, and make this matrix becomes stronger. And that's why when we transmit the wave here in this the first phase, we're not going to have any way traveling, any shear wave traveling, because the waters, most of them is waters, and does not carry any shear wave. But at this stage, when they are they own the hydrated cement, they breach on the particle and on the aggregate with each others, and then the way it's easier to travel between them, and then that explains why we have a higher penetration resistance, and also we have a higher uh, energies of the liquid Rayleigh wave. So that's is the principle of technologies. Now is the time in order to run the test to verify the technologies. So my hypothesis is in this study is the initial time of the liquid Rayleigh wave going to be similar to the times of the set time that determined by the ASTM standards. So in the lab, we make 6 different mix. And then you can see that we mix with 2 water cement ratio. One is 0.39, and then the other one is 0.5. And we also including in each mix, we have 3 different type of chemical mixture. Sorry, 2. And one we don't add anything, just the plain cement. And the other one we have accelerators, and another one we have the retarders. And all of them we run the test with the pin penetration test, ASTM standard. And now here's the result. And then on the left figures is the figure showing the correlation between the final set times that we determined by the ASTM standards. And then the bottom horizontal is the initial time that we determined by the non-contact technologies. And as you can see that the dashed line showing the correlations between them, and it's almost is a 1-to-1 ratio. And with the very high correlations R squared coefficients. And then another result that we have is showing on the right figures, where in these figures, we trying to compare between the initial time of the Rayleigh wave vary by the Watson ratio, and also vary by the chemical admixture that we add into the materials. So here in the plain mortar, we have 2 water cement ratio. And we can see that, as we know that the higher water cement ratio is going to give us a higher setting time, right? And then this rule is correct for all the mixtures. So with the plain mortar, with accelerators, and the mortar with retarders, all the higher cement ratio give us the longer set time. And another thing is the effect of the chemical admixtures also reflects here. So when we have the plain mortars and when we have an accelerator, it's reducing the set times. And when we use the retarder, it's increasing the set time. And then using the non-contact technologies, we see that it's very good, in a good agreement with all the hypotheses and then the rule that we know by the water cement ratio or by the chemical admixtures, right? Oh, I already described this. And then finally, after we run many tests in the lab, we try to use the techniques to see that how this technique going to work in the field. So here is that one of the projects that we try in is the CRCP pavement. It's in Itasca near Chicago. So this pavement, it's including the 5 sections, and then we choose to test only 3 sections, which is 1A, 1C, and then 1D. And all the sections here, they have a same mix design. That the key point here is those sections were cast in different times of the day, and then at different day as well. So what it means here is the set time of each section can be varied because that the temperatures, the humidities, and also about the moistures of the environment can affect the set time. And when we apply these technologies, we found that the set times is really varies between them, even though on average it's very close to the set time that they run in the lab. But this result is it's point out one thing that set time can vary a lot over section or over the whole pavement, because that please keep in mind that we have in the field the moistures, the temperatures, or the humidities keep changing uh, over time. And then using these techniques, we hope that we can map the whole setup of the whole pavements uh, in order to predict next construction activities. So with that, I will go into the next section where I will talk about some application of using the non-contact technologies, including predict the socket timings and evaluate the curing compound effectiveness. So I think I just want to go briefly about why the socket is so important. Why the socket timing is so important to the quality of the pavement. So the plot is showing here is the vertical is the damage, and the horizontal is the time that we do the saw cutting. So let's say if we do the saw cut, I think there's nobody going to do this, but if we do the saw cut at the too early when we mix the concrete, we're going to see it's very small or little of raveling and spalling because that we cutting is still in the liquid phase. But over time, when we cut it early, this window is early, we will have a lot of the raveling damage as it keep increasing. But at some point, when the concrete materials is strong enough and we can resist the saw cutting, you can see we have a less and less raveling damage. And then we will go into the window that we have an acceptable raveling damage or it's not even visible. But if we keep it too late and we do the socket, it's too late. The good point is we have very nice cut, but but the bad point is that we might be already too late. And what happened for the too late skull cutting is we're going to have a lot of random shrinkage crackings appear over the surface, right? And on the pictures I'm showing here is that some damage causing by the saw cuttings that when we do saw cut too early and we do saw cut early or maybe we do it on times and then one we do it very late that we have very nice saw cut, but this one might indicate it that we are out of the window and this might create all of the transverse cracking, random transverse cracking over the surface of the concrete pavement. So we had to do something in order to know that about the time that we need to do to evaluate that the time that we do the socket is mean that we have to evaluate the qualities or the spalling damage after we do the saw cutting. But what we have, sorry. So the existing quantification techniques we have so far is not really quantitative. All we have to have the ranks from, it's called a JRIs, that index that we use. It's very qualitative. It's range from 0 to 3, but all they do is they have a coin or the quarter they put right next to the socket, and they compare between the spalling damage with the size of the coin, and then from there they evaluate the index of the ravelings. So so in my lab, what I want to do is I want to use some techniques that I can determine that the socket window that I'm showing in this plot. All right. So what I do is I make a concrete block that's showing here, and it's the size of this concrete block is the 500 and the depth is 150. 500 by 500 and the depth is 150. And then what I do in order to determine the right socket timing is I will make a different cut at different times. The intervals between them may be 30 to 60 minutes, and I keep cutting until I find until I see that I have acceptable routing damage, and then that is I call it a socket timing. And here I make 6 different mixtures. Again, just similar to the previous study, I changed the water cement ratio of 3 of them. Now I use 3 water cement ratio 0.39, 0.45, and zero point 0.5. And also I use and uh, and then I run the test using the non-contact technologies in order to determine the final set time, right? And after that, after doing the cut, at every cut joint, I will quantify the damage of the spalling, not using this method. The method I'm coming up with is more quantitative in order to know exactly the spalling damage. So the method I use is just use the phone cameras, and I take a lot of pictures of the socket. Here you can see that this is the slab 500 by 500 by 150, and I use my phone in order to capture a lot of pictures along this socket joint. And what I did here is after I take a picture, and then I will detecting the spalling or the raveling damage along the joint, and then I construct the 3D model in order to calculate the surface areas. The reason I calculate in the 3D model is because that we will have more perception of the depth of the spalling instead of just using the area in the 2D image. Right? So with that, just like I mentioned, I make a socket at different times on the slab, and the purpose of doing that is in order to to build the raveling damage progress over times, as you can see in this plot. Right? As you can see, is initially it's have a very small intensity of the damage, but over time, when I keep cutting it, the damage is increasing, and at some point the damage is reduced and it's become more stable. And then I repeat that technique for all the mixture that I have in the lab. And here is from the damage in order to compare between uh, different slab. And then so I had to after I quantify the surface area of all the damage here, I divide it by the total area of the socket joint. It's the fixed numbers in order to obtain the raveling damage index. And I use this index in order to plot the profile of the damage of on the mixture that I make. And then you can see that one point I want to point out here is that the yellow box here is the set times of each mixtures. And most of them showing that if we do the saw cutting before the set times, will we have a chance to create the maximum damage, the raveling damage to the pavement? And that happened for all the mixture that I observed here. And another, so why we have to do that the saw cutting after the set times? And you can see after it's set, the uh, more energies of wave energy is traveling. It's indicate that the concrete have more shear or more strain developed in the material. That's why it's strong enough in order to resist the saw cut, and then that's why we see that when energy is increasing, it's the time that the damage starts to decreasing significantly as well. Okay, so when we plotting this plot, we want to predict that the correlation between the set times and the time that we have some certain damage or intensity. So, and we know that the set times that we conduct by the non-contact technologies is strongly correlated with different raveling intensity. So, for example, like here, in order to have 10% of the raveling damage, we can also control it from the socket timings. Sorry, from the non-contact technologies. And then in order to have 5%, we can also use the set time from the non-contact and also 3%. Then the problem we have here is we don't know if is or either 10% or 5% or 3% will be accepted or will be acceptable by the socket operators or by the field engineer, because at this moment we don't have any guidance or standard saying that what is the acceptable damage for the socket joint. So that's one thing that I did is that I conducted a survey on 10 different joints in order to find the acceptable raveling index using the same technologies that I developed in the lab. And it turns out for all the socket that I found in 2 different sites is the on average is 3% is the raveling damage that they have in the field. So that's why I use this 3% as the acceptable number to indicate that the raveling damage accepted by the saw operators. So it turns out that in order to get this 3%, all we have to do is just use this equation that that determined by the non-contact set times. What does it mean here? This equation telling me that, for example, using the non-contact testing, and we determine that the final set time is the 4.5 hours. And all we have to do is we just have to wait another 2 hours more and then start to do the saw cutting. And then that time we will get the mostly we will get the 3% of raveling damage index. And then it is according to the survey that I did in the 2 sites, it will be acceptable saw cutting, right? So I will talk about another application of the non-contact testing. So here is we trying to evaluate effectiveness of the different curing methods. So in the lab, we make 3 samples. On the left is the sample with no curing, and the middle one we use with the curing compound, and on the right one is the sample that we kill with the plastic sheet cover. And then here is the one example of the hairline cracking that happened to one of the sample. As you can see here, there's a lot of hairline cracking happening on this surface. And if I zoom in this area, you can see hairlines happen everywhere over the surface here. So, and other than the visual inspection, I also did the water loss in order to quantify the effectiveness of the curing compounds. And it's the result showing that without no curing, the water loss is really high. It makes sense because that the waters evaporate and it's reducing the weight of the samples. And then for the curing compounds, it's for the plastic cover, it's pretty good, but among the 3 cases using the curing compounds, it's give the best result, right? And then using the non-contact technologies, we obtain the similar result with the water loss test. And as you can see here in the no curing on the left side, plastic cover and curing compounds, the non-contact technologies is quantifying the damage, the surface cracking damage due to the water loss. And then here, the principle of this method is it's capturing the wave propagating forward and capturing the wave propagating backward. As you can see, if we have more crack over the surface, when the wave traveling, it will reflect back more than it moving forward. So in this case, that we can see that on the left half is the wave that the total wave energies that move that reflecting backward compared to the wave moving forward. And then you can see the total area of these really high compared to the plastic cover and the curing compound. In the curing compound case, most of the energies is the moving forwards because that we have less crack happening over the surface. And this test is a very good agreement with the water loss test that we did previously. And it also show that using curing compound is the best method in order to uh, for the to ensure the hydration of the concrete materials. So with that, I want to make the summary of my studies. So as I can as you can see that using the non-contact, we can uh, not only measure the set time of the concrete materials, but also we can evaluate the curing effectiveness of the curing compounds, and we can use these technologies in order to predict the sock timings. And then also after we do the socket timings, we can also quantify the raveling damage intensity using the camera as well. And the one of the study that I don't show in here is that we can use we can use the mirror if you are interested in the 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 the, the crack activation below the socket joint. You can use our algorithm that I developed for CPTech Center that we use the mirror in order to verify if the cracks below the socket joint is deployed or not, right? So we already build all an environment in order to determine from the set times, predicting saw cuttings, and then also to verify the saw cuttings. So the future study that I want to do is we know that whatever we do right now is to enhance the quality of the earliest pavement, and then by doing that in the good time, right at the initial, we can ensure that the performance on the service line and reduce the life cycle cost of the pavement. And then one of the study that I want to do is I want to see that how much that I can improve in terms of the performance or the service life or the life cycle cost if applying these technologies to the pavement. And then hopefully in the futures I can implement these techniques when attached into the paver, and then when the pavers is paving the concrete material into the pavement form, and then I keep when it's moving, I can keep scanning the whole field of the pavement and then map the set time of the whole pavement at the same times. That will be the future study that I'm going to do. And with that, thank you so much for listening to my presentations, and I'm very welcome to your suggestion and then comments. Thank you.
Thank you. I have not seen any questions or comments in the chat. So if anyone would like to unmute and ask a question directly, you're more than welcome to. I do see a hand from Bernard.
Yes, I do have a question. Yeah, thank you for such a very decent presentation. It's good for us to look into these technologies. One thing I wanted to ask you to clarify for me is your raveling index. Why did you choose to call it raveling index? Why not spalling? I thought those were sliver spalls.
Thanks for question, Bernard. One of the reasons we choose the name raveling is because that spalling is more related to the later state than the early state. So ravelings, initially we choose the word spalling in it to be more general, but then we found that raveling is more related to the early state damage than spalling. That's why we think is that raveling is more suitable in word to use in this case.
Okay, well, raveling became quite popular in concrete when we were losing material from pervious concrete, losing surface material. But we know that one of the things we had to deal with in early sawing were the sliver spalls that were occasioned by the early sawing. Well, just a thought. Maybe semantics. I have a second question. Where do you see? How do you see success in this technology? Is it when, for instance, it has grown to a point where every inspector has the technology in his hand? Where do you? I mean, how do you envisage success in this initiative?
How do I see the success in these technologies? When you say the technologies, you mean the non-contact ultrasound, or
Yes,
you
yes,
okay.
non-contact, yeah.
So this one I believe it have a lot of potential to for success, because so far I haven't seen that any techniques that it can help to map the whole field, the set time of the whole pavement. I see the smart rock, and I see that another technologies pretty new recently from Purdue, um, which is similar to the smart rock, that you use that sensor and then you embed into the pavement. But most of but again, those sensor is pretty much that you have to embed at certain locations. So what it means is that you can only measure the properties at that location only, and it's not reusable. So the non-contact it's open to the new field if you want to measure the properties over the wide range areas. And then if you want to use technology again and again in different projects, in that sense, in these technologies is really useful for that purpose. I hope that I can answer that I did answer your question, Bernard.
That's fine. Thank you. Thank you.
Any other questions from anyone? Feel free to use the raise hand function or just unmute and ask your questions or comments.
Yeah, good morning. This is Neat Technology. This is Ross Benson, working with the Illinois Tollway. I got on late, so I don't know if I missed the information. What's the cost of the, sensor and the recording of, all of the information, all of the equipment that you need to do this?
That's a very good question. So right now, I don't know exactly the cost for these sensors yet. I hope it will come soon in the near future, but I cannot answer that question now. We still
All right,
yeah. Sorry, go ahead.
Oh, that's good. This is Jamie. Okay, thank you. Thanks for the presentation. Jay Bankey with State Testing, also part of the Illinois Tollway Group. So I guess my question is, who do you see as the end user for this technology? Would it be literally like the saw cutting, subcontractor that's out there? Initially, yeah. Who do you see most benefiting from this?
Well, for these technologies, I think that the field engineers will be very beneficial for these technologies, or maybe also the saw operators. So imagine if you have these technologies, for the field engineer, they can verify the set times, right? And for the saw operators, um, they can for example, they can measure the set times, and they don't have to wait there in order uh, to know. Like I don't see the reason why people have to wait in the field for a couple hours just to wait until the time that they had to do the saw cutting. They what they have to do is they just have these sensors. They capture the set times, and they have the empirical equation that we provided, and then from there they know exactly when the time they have to come back in order to do the saw cutting. And right after they do a saw cutting, they can apply the technology in order to quantifying the spalling damage, and then document it, and then send it to the field engineers and say, hey, so we done the saw cutting at the right timing that we at the right timing after we do the predict the set time, and also here is the spalling damage that we quantify. So between them, there's no conflict at all. And also I want from this study, I really want to have a guidelines or some standard that everybody agree on what is the acceptable Revlon index in order to have a good saw cutting, with respect, of course, with respect to the spalling damage, and also with respect to the time or the respect to the activation of the saw of the crack below the saw cut, right? So yeah, so again, so I think the field engineer and the saw operator will be uh, beneficial from these technologies.
Okay, well, thank you. I guess my point on that would be, I don't know if I'd be comfortable. It sort of falls under a means and method. I agree for the saw cutter, the operator, it's definitely got potential and benefit, but as more of a field engineer, I don't want that responsibility to tell the saw operator, yeah, go ahead out there and saw and cut it now, because at the end of the day, you're right. We don't want any spalling or raveling. I want a clean cut joint, but I want to leave it up to the contractor to do that. And I really don't want the field engineer to have that, responsibility, right?
Yeah, in that sense, I don't have enough experience now to say exactly who gonna need that, but yeah, well, yeah. But thank you for the questions and then comments.
We did get a couple of questions in the chat here, so I'll try to read those off. Could the non-contact technology be popular like nuclear densimeters, compaction tester one day in the future?
I really hope so. And we've been doing really hard in the lab in order to make these technologies is better and better. And then we hope. I'm really open for any DOTs or any contractors that um, that give it like we can demonstrate this technology in some concrete pavement that they have been doing or they will do. And we can clearly show the benefit of using these technologies. So that will help us in order to populate these technologies, and hopefully it will be successful in the future in one day. So another question I have here is, did you try modern frequencies? Was there one frequency where the correlation improved? That's a good question. We did not try a different frequency because the transducer we got is not able to change the frequency. So, like I said, right now in the lab, we try a different frequency in order to see that if we have a better correlation or not. Yeah.
All right. Well, we are running out of time. But I see one more comment here. I like the 3% raveling as an acceptable balance between raveling and not getting in time. So I think we will wrap it up for today. But thank you very much, Dr. Tran, for your time and your presentation, and for all of you attending today. I will get this recording up online later this week if you want to pass it on to any colleagues that you think might be interested. So thank you very much for joining us, and we hope to see you next time.
Thank you.